I'm a Senior Vice President of Automotive in AEye. And as Andre already said, I have spent most of my career in big Tier 1 corporations, many years in driver information, as you see, mainly in JCI and Visteon, before I joined Valeo, where I've been the last 6.5 years, and where Valeo basically became a multi-billion ADAS business. And so I decided last year to move to a Silicon Valley startup. I must not say that we are still a startup because we are publicly listed at the NASDAQ, obviously, since August last year. But reasons were really a unique business model and a unique situation with Continental as one of our Tier 1 partners for ADAS and autonomous mobility. Today, I like to talk about the software-defined car, the new business models, and the impact which can be made by an adaptive and software-configurable Lidar. I believe that it's time to retire the conventional wisdom that a car loses value when someone drives the car out of the dealer's lot. With all the technology advantages we have over time, which we know from the smartphones, this change is really driven by the growing prevalence of software within cars and the ability to upgrade that software over time and to add new features. In this way, new cars are becoming no different than phones. You have heard it today, smart fridges or any other connected device. And the rising expectation from consumers is that the underlying software in everyday hardware will be regularly updated with new functionality and features without them having to buy a new model for that privilege. Obviously, this trend turns the traditional automotive business model on its head. You know, historically, many consumers replaced their vehicles every 5 to 7 years as automakers introduced new features. But moving forward, instead of buying a new model, consumers will be able to get value-added features via software. Why should a car lose value from the moment when it's moved out from the dealership? There's no reason. The car can become even more valuable, ideally, over time, like a smartphone, when you will add apps and over-the-air updates. As you see, Lidar usage is now spreading beyond specialized vehicles, and they are running more into, let's call it, run-of-the-mill safety features like lane keeping assistance and automatic emergency braking. In industry parlance, these are advanced driver assistance systems, which we call ADAS, but they are quite separate from autonomous vehicles, and we heard about that in the morning too. The additional sensor input can help improve reaction times and accuracy for these features, but of course, we know it, there are hardware costs adding to it. I think you have seen these pictures. Technologists, Hollywood, have promised us autonomy for decades, but the reality is far from the promise with AVs which are limited to geofence deployments. Why aren't we further? We know our needs in the cars. It's big touchscreens, big digital clusters, constant internet, better navigation, music streaming, mobile key, remote operations of the vehicle, and retaining a similar experience as we have with all our smartphones. But the other highly demanded technology is autonomous driving. They are really a step up over simple driving assistance systems like lane keeping or adaptive cruise control. At the end, we are combining all these sensors to a hands-free experience. And you have seen a lot of examples, prominently, obviously, this morning with George presenting the Mercedes S-Class, but you know it from Lucid, Dream Drive, Tesla, FSD Beta, GM Ultra Cruise, and others, which are basically following this way. Conventional LiDARs are not able to support these new business models as we move from hardware-defined vehicles to software-defined vehicles. But what is a software-defined vehicle? Let's first talk about the definition before I make the link to a software configurable Lidar, which will enable the development of this software-defined vehicle. I think you all have seen this kind of vehicle architecture evolutions. It's a natural evolution of the vehicle, which is caused by digitalization and evolution of the computer hardware. SoCs, which consist of highly integrated CPUs, memory, and peripherals, are multi-purpose and powerful enough to handle not just single tasks, but multiple. So because of that, there is no need to have dedicated ECUs per vehicle component. So we will only have powerful, few centralized units which can handle multiple domains and various sets of sensors. So this transformation to a software-centric approach improves agility. We've heard about it in the morning, and it further enables the reusing of a common platform. The software-defined car is one of the core steps within the current automotive industry, the digital transformation. And this means as well that we need to rethink on the way how we are developing this car. I think the times are over, and it cannot be any longer managed, the complexity where we have 100 ECUs, complex networks, and non-standardized communication interfaces, which will be consolidated. And so they will be consolidated. And the way how this will happen, I make an analogy to the way how smartphones are developed. The industry needs to rethink this car and its development. The conventional architectures, they will die, and the OEMs will learn and adapt their development processes with what, for instance, Apple or Google have demonstrated over the last decade. And there's endless benefits of the software-defined vehicle. For instance, new services. In the future, they can be activated individually according to the driver's needs. Temporary services, features, or apps. We can talk about new contract and pricing models. We can talk about features provided as a service, as a subscription, or even as an individual purchase. Second, continuous connectivity. So the vehicle can communicate with its environment, collect data in real operation, and send it to the cloud. I think from AWS, you have heard it today, how this will work and how this can benefit to the development of the software-defined vehicle. And then the increased vehicle value. Just like with a smartphone, drivers expect new features to be continuously available for their vehicles. And this challenge presents as well new opportunities. So with regular updates, the value of the vehicle can not only be maintained, but it can be as well increased through the entire life cycle. And this means we have to learn from this industry. We have to learn from the Apples and the Googles how they develop software. And you can see these similarities between a modern smartphone architecture compared to the software-defined vehicle. But what are some of the implications of this shift? First, automakers will need to put software features front and center as part of their value proposition to bring in more revenues and increase margins. They are certainly not slacking on building a software foundation. A few examples on that. The new car has about 100 million lines of code underlying its operation. A Boeing 787 Dreamliner, for instance, has 14 million lines of code. And just for the sake of curiosity, the Apollo 13, 50 years ago, used 64 kilobytes. So many OEMs, they are pushing already vehicle software that follows the pioneer Tesla, which was the first company, I guess, doing software-based vehicles that support over the air. So now many OEMs are planning that, be it the Mercedes OS, the Volkswagen operating system via Carriot, General Motors, Toyota, or Stellantis. Let us first have a look into Tesla. And now I come to the business aspect. Traditional automakers, typically they grow their top line probably 3% annually. Tesla is growing more than 60%. And it's not only that the users want to have a nice car, but they want to have services and software. And these software revenues, they are a real cash machine. And analysts at Morgan Stanley, they really say that they could even make more money from the software they sell than they get from the hardware. So this is a real tremendous shift of the business models. So now, why do I talk about Lidar? And we know exactly that Elon Musk is not a friend of Lidar. But he could reduce the number of fatal accidents to reach the objective of 0 deaths caused by cars. Therefore, let's have a closer look to Stellantis to make the link to the business model. I quote now the New York Times. They said basically, within a few years, Stellantis hopes to be able to offer new feature on demand that customers can buy to upgrade to their vehicles, such as hands-free driving, better performance, or improved handling. It also hopes to sell communication services to enable drivers and passengers to handle more work tasks while on the road. So this is original Stellantis, and the automaker expects this strategy to generate 22 billion euros software services and subscriptions. So this is a massive number, and we have seen similar announcements from all the other car makers. I believe that the pieces are really in place for auto companies to embrace this new business model that rely on unique subscription services to drive revenues. But the model only, I would say, withstands if the underlying technology enables it. Think of highway autopilot, which might be purchased either through a one-time or monthly fee. Or drivers could upgrade an existing safety feature, such as adding a redundancy of Lidar to an application like lane centering. Can you imagine what it means if they could help to qualify for an insurance discount? So we have to really think out of the box. So as the software-defined hardware absorbs this new technology advancements, the innovative services they can be offered, they are expanding as well. The question is, are there any potential pitfalls? In the days when software updates could only be delivered by bringing a car into a service center, there was a valid concern that the software would be out of date the minute the car rolled off the lot, and that any potential bug or critical software patch would remain unaddressed for months at a time. Did you have that in your case? I remember I had this, definitely. But in an age where software updates can be delivered to vehicles instantaneously, in the same way they are delivered to billions of smartphones and computers every day, I believe that this concern can be neutralized. This is really a real innovation in the auto industry. The more a consumer's perception of value shifts from the hardware itself towards software-based features, the more that automotive companies will need to focus their efforts on this front, because those features will help them differentiate and drive business growth. Let's now close the loop between the software-defined car and the AEye software configurable Lidar. As you can see in this chart, and I thanks to the researchers of Yole who are providing this report on a regular basis, new sensing modalities, including Lidar, will expand both assistant and autonomous driving features over the coming years, including customer-critical functions like highway pilot or traffic jam pilot. A software configurable Lidar will provide benefit over the entire life cycle of the vehicle. And it starts at the concept phase, it goes through the development cycle, it starts when the OEM starts to collect data, and it goes much beyond SOP when it comes to regular rollout of new applications and improved functions. As a consequence, we claim that we are supporting these new software-driven business models of the OEMs, be it for feature updates or enhancements or for new functionality. The software configurability of the AEye Lidar helps to keep or increase the value of the car over time without changing or validating new hardware. The question is, why did we decide for this architecture? And it goes back to Louis Toussaint, one of our founders and our president, who was coming from the military and defense industry. And he basically is transferring the principle of what he has done for all the fighter jets in the defense industry. They are still today in every starfighter. It is embedded. He has basically kept the dream to transform this technology into the automotive industry. Typically, where we always look for compromise in regard to range, resolution, field of view, or frame rate. What are the challenges for such a LiDAR? And there's, of course, multiple. We have unpredictable objects. So the LiDAR, of course, must have the range and the field of view needed to detect and begin tracking the target, and early enough. Then roadway obstacles, obviously. Can they be overridden? So we need resolution, we need range, and adverse weather conditions, obviously. So the LiDAR must have the flexibility to respond to these changes, be it driven by weather, by the location, by the speed, by the driving scenario, or by any other external perception cue. And the answers for that is basically in our architecture of the product. Creating a LiDAR that meets every requirement all the time introduces unacceptable trade-offs, and you know it. Whoever has defined a LiDAR at the OEM industry, typically you are asking for different KPIs, and then you make a kind of trade-off in between the different parameters you have typically from the OEM in order to define and specify the product. We have 4 levels of advanced functionality that enables the system to dynamically adjust the operating mode. And this is based on different scan patterns we can adapt in our product. So what is the approach? As I said, we have applied sample principles used to design mission-critical targeted systems for fighter jets to create the highest performance sensing and perception system for self-driving cars. How do we do that? We do it through a modular software configurable system architecture that employs deterministic artificial intelligence processed at the edge of the network. But this means as well a new way of thinking how OEMs, and this is what we want to drive today, how they are specifying the requirements. Because we see more and more that the legacy approach is not any longer valid for these software-defined vehicles. Makers of automotive LiDAR systems, they are basically frequently asked, and I get these questions every day, what is your frame rate? Can you detect objects at 10% reflectivity? Can you meet 250 meters? And so on. We believe that these benchmarks, they are required, but they are insufficient as they don't capture the critical details, such as the size of a target, the speed at which you are getting close to the target, or the cost of the information. We believe that it would be productive for the industry to adopt a more holistic approach when it comes to assessing LiDAR systems for automotive use. What is our argument? We must look at a matrix as it relates to a perception system in general, rather than as an individual point sensor. And then, as a consequence, ask ourselves, what information would enable a perception system to make better and faster decisions? So what do we propose to the industry now is that we turn this old process on its head, as we do provide answers to your functional requirements, rather than building a fixed and static sensor where functions must be built around respecting the limitations of such a hardware. With the ability to create certain performance modes, we can provide the best operating mode for your requirements. And this is basically what I would like to discuss, of course, with the OEMs tonight, hopefully at a nice glass of whatever. Yeah. So what are the current performance modes? So I think here we have a couple of examples. And what we see here is that a current autonomous vehicle sensor configurations typically uses a combination of Lidar, cameras, ultrasonics, and radar as their senses. And we do not compete against these technologies. It's a comprehensive technology. And but basically, every data, they are collected serially, and they are limited to fixed patterns of search. And these senses collect as much data as possible, which is then aligned, processed, and analyzed. This post-processing is not efficient and does not allow for situational changes to how sensor data is captured in real time. You know it, 90% of the sensor data you collect is thrown out as it's either irrelevant or redundant by the time it is processed. Can you imagine at highway speeds, this latency results in a car moving more than 20 feet before the sensor has been fully processed and throwing away data you don't need with the goal of being efficient is, in our opinion, inefficient. The better approach is to have a software configurable scan pattern, which you can choose depending on different situations. The optimum performance mode, be it highway, where we can see, for instance, 500 meter and beyond, and we have demonstrated it, or be it in urban mode, where we don't need the longest range, but a higher resolution at a bigger horizontal field of view. Let's close the loop why a software configurable Lidar has unbeatable advantages for the development of a software-defined car. I would like to start with a simple diagram and then show you a video demonstrating some remarkable capabilities that have never been shown before. On the left of your screen, you can see an illustration of how many traditional passive LiDARs work, not to say all. They collect data in a fixed serial manner, which they then pass into the perception engine. It's a one-way flow of data from a sensor into an application software layer. The idea being to collect as much raw data as possible and turn it into information later. It can be a challenge, especially at high speeds, and we know it. What you see on the right is that we took a very different path by building a software platform on the sensor, which gives us unique capabilities. We can now control the hardware by using software to change the way the sensor works, depending on different environments or the use case. Secondly, we have added a feedback loop between the perception and application software and the sensor software platform. And this allows the applications to ask the sensor for the information which is needed and which will improve the information quality. And on the right side, you see that it's not siloed, it's from other sensors. We can use maps, cameras, radars, or IMUs to trigger the LiDAR so that we can be more intelligent and efficient. So finally, this software-defined architecture is natively compatible to enable over-the-air updates so that we can change the scan pattern and that we can completely be able to upgrade new features and functionality. Let's have a look into the video. So I told you that we have multiple performance modes which allow the vehicle to be situationally aware and to adjust depending on the application, environmental conditions, or the maneuver the vehicle is trying to perform. Please keep your focus and your attention to the icons on the middle of the screen. This will show you how the car is changing the scan pattern to support different driving scenarios. When in urban mode, range is reduced as resolution is increased on the sides to detect lateral entry of pedestrians or other vehicles entering your path. Then you have lane changing mode. It puts more resolution on the adjacent lanes. And finally, as we shift into highway mode, where speed is increased, the Lidar extends the range and the density on the road surface to look for small objects which needs to be avoided potentially. And what you see in the bottom of the screen is a traditional point cloud that the computer sees. I hope that this was at least a bit helpful to provide the understanding how this adaptive sensing platform can provide a higher quality information than a pure hardware-defined legacy Lidar. Let's wrap up and summarize the presentation. With one hardware, we can create multiple scan patterns. You have seen multiple use cases, be it urban, be it highway driving. We can do it with one Lidar solution. Over-the-air updatability to roll out improved features, to enhance features, to bring new features. It's possible. But a very important factor is as well that the cost for verification and validation finally will go down, even if maybe the initial invest might be higher for a Lidar, which we all know it's an additional sensor. But with the new software business models, and especially using the step-by-step AD functions the OEMs are providing, we can make usage of those sensors as well to improve the ADAS. And then a business model is possible for the OEM, for the tier, and the OEMs will benefit from a better user experience. With that, I'd like to close my presentation for today and like to say thanks for having had the opportunity talking here. Thank you so much.